はい、じゃあ始まります。これでいいのかな。 OK ですね。はい、始まります。それでどうやったらいいの。私がツイッターで古賀先生です。それでこれでいけるかな。第10回3月6日日曜日9時開始です。それでコンパスとブルーキャットあります。コンパスのページここです。第10章のパート1から。それでそうか、ここに載せてないのね。これ載せなきゃいけないんで、イベントを編集する。それで、ここか。ここに載せますと。どうやって載せるかというと、これを、載せます。で、ページを、それでブルーキャットの方にも載せます。これなんかおかしいな。編集でここに載せ、リンクをつける、セーブで、こっちにも載せるで、セーブ、あれ違うか、更新ということです。いいかな。それで本はここにある Amazon にある、クォンタムメカニクス by サスキンドです。それからテキストはここにあります。で、これを開けば OK ね。それで311ページから311ページからなんだけど、あれ311ページ、ここのそのちょっと前の復習をやりたいと思ってます。で、ちょっと考えてたんですけど、この本を超えることを、説明してもしょうがないので、本に書いてある範囲にとどめたいと思います。これはなんだ、これ誰かのやつかな。はいはいはい。それで、経路積分、パースインテグラルの話です。でパースインテグラルなんだけれども、結局、あれですね、なぜかちょっと時間を縦軸に書くんだけど、横軸が X ね。こういう風に書いて、X1 から X2 まで、時刻は T1 から T2 まで。で、古典粒子の場合はこの中をなんかこういう風に軌跡を描くと、トラジェクトリーを描くってことです。それはニュートンの 運動方程式によって、この奇跡が決まるし、最小作用の原理、作用アクションっていうものを、ラグランジアンのアクションは、ラグランジアンの時間微分 t1 から t2 までラグランジアンは x ドット、この時間積分をしたものが、これが定流点を持つように、xt というのが決まると。この1、2から3が決まると。それがこれ古典ね、クラシカルで、こういうふうに決まると。で、クォンタムメカニクスの場合はパスインテグラルというのを考えます。So then we know that initial state is x1, then time is t1, then final state is x2, t2. Then in between we have time evolution. Time evolution is exponential I h t. I forgot if there was a minus. I think there is minus. Path integral. Minus. Okay, so then we actually have identity operator, which looks like this. You integrate from minus infinity to infinity dx, then x. This is the identity operator. Okay, so then we actually we can break this one. This one, like okay, maybe just 3 part. I can put E to, let's see, how do I do E, no, sorry, this is minus I h t2 minus t double prime. Okay, we can have this E minus h ih t double prime minus t prime. Then we have E ih t 1 prime t. So we just we had this one ih t2 minus t1. We just separated this factor into 3. This way. this is a product. This whole thing is a product of three parts, separated by t prime and t double prime, for example. Okay, so then you can actually insert this identity operator. やり直す。取り消す。Okay. We can insert identity operator to here and here. Yeah. So then, to avoid confusion, we can put x something like this. So in this picture, the point is insert identity operator is here. T double prime, T double prime here, T prime. We inserted two places identity operator. Then what we have is something like this. Let's see, I don't know if I can write. I kind of have to remember this. Okay, so this is the probability amplitude. We have x2 t2 exponential minus IH t2 minus t1. T then x1 t1. Okay, so this will be, and this is dummy variable. We use two dummy variable.積分変数. How do you say 積分変数 in English? You can put minus infinity to infinity, minus infinity to infinity. Then you have x2 t2 e minus IH t1 minus t double prime. Sorry, this is look ugly. T2. Then here is x. Let me switch this. It's same thing, but same. Just x double prime t2. No, t double prime. Yeah. Then let's see. We have x double prime t double prime exponential minus IH t double prime minus t single prime. Okay, then we have x single prime t single prime x single prime t single prime exponential minus ih t single prime minus t1. Then we have x 1 t1. Okay, this is a probability amplitude. If we insert two identity operators, yeah. So then what happens? We can insert as many identity operators as we want. We can freely insert as many identity operators as we want. So we insert n identity operators. Then what happens? We have, let's see, I need to change subscript. I have to change subscript. 2 is 1 2 is not good subscript. We do final state and initial state. Let's do this initial state. So this is initial, then this is final. Okay, so then we insert n identity operators. So what happens is we have integration dxn dx1. Okay, then we have xf tf e minus ih tf minus tn xn tn. Yeah. X. This is I use. Was it okay? I don't know. I think I should go this way. This one. Was it okay? I don't know. It's working, eh? I think it's working. So this is more like here. xn tn exponential minus ih tn minus t minus 1. Yeah. x n minus 1 t n minus 1. Okay. Then we still then final one is x1 t1 exponential minus ih t1 minus ti, then xi ti. Okay, so then I have to change subscript again, I think. I'm sorry, I have to change the subscript again. I change this final one, instead of f, I change this to n plus 1. N plus 1. Then this one, this guy become n plus 1. Okay, so then I hope this, let me change. I can do this n plus 1, and here n plus 1, then this guy I can do n plus 1, then I can do it like this. Okay, so this is better. So then here I change. This is 0. So I decide to change I to 0. Okay, so this is good. So then, what is the thing? This we can set this difference to delta t. That's okay. Yeah, so we can change. We can the minus x plus minus infinity to plus infinity d and d x n minus infinity to plus infinity dx1. Then we have x n plus 1 t n plus 1 e minus ih delta x delta t xn tn. Okay, so then x small n, t small n, exponential minus I delta t, x n minus 1, t n minus 1. Then we have x1 t1 e minus ih delta t x n minus x0 t0. Okay. Then the question is, which one is u? Okay, this textbook called C12 is like this. So this is called u. So he didn't insert identity operators. Okay, he just called this one, this thing. He used epsilon. Okay, not delta t, but he used epsilon here. Epsilon here. Okay, then what he called u is this one. This thing is called u. So this thing is called u. This thing is called u. Then he didn't put identity operator. Okay, so he didn't put identity operator. So because he didn't put identity operator, he does not need this integration. He does not need this integration. He just have x n plus 1, t n plus 1, then u x0 t0, and these things is actually just exponential ih t n plus 1 minus t0. So this has to be capital M. Okay. We can then insert identity operator between the u's. Okay. So the procedure is you insert identity operator between u. Here you insert I, insert I, insert I, insert I. So then what you will have is something like this. Just what I write. You will end up having this thing. So you will end up having this. Then such an expression can be called the amplitude for the given path. This is okay if you don't integrate. Okay, if without without this integration, see, this is this whole thing. This is the amplitude for given path. Yeah, you can see the picture. There is this way. So you just have zigzag path. Whatever you like. You can have any zigzag path. Zigzag. Doesn't have to be zigzag. You just you can draw any path, something like this. Any path, but because now you will finally has to integrate these over these intermediate x. This x go to infinity plus minus infinity. Only this end points here and here is fixed, but all intermediate position has to be integrated. So you will take all kind of paths after integration. But without integration, you can call this one, you can call this black, this thing, because here intermediate point like xn minus 1 or xt, x1, x2, x3, blah 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 to xn are all fixed point. So this is the probability amplitude for a given path. Yeah? Then if you integrate like this, if you include this integration, you will have a probability amplitude for particle at x0 at t0 go to xn plus 1 at t n plus 1. The whole probability amplitude can be obtained by integration. Anyway, so but the particle does not travel along a particular path. Instead, in the limit of a large number of infinitesimal time intervals, the amplitude is the integral over all possible paths between the end point. The elegant fact that Feynman discovered is that the amplitude for each path bears a simple relation to a familiar expression from classical mechanics, the action for that path. The exact expression for each path is, so this is interesting. So this is something like this. This actual more precise meaning of this is actually this is e to I a goes like this: x n plus 1 t n plus 1 semicolon t semicolon x n t n, yeah, semicolon da da da, semicolon t1, sorry, x1 x, oh, x1 t1 semicolon x0、ほい、x0 t0。 Does it make sense? Divided by h bar. Divided by h bar. So this action depends on the trajectory chosen, and the way we choose trajectory here is by this inserting n identity operators. But we do this. We just do this. We let n to infinite. Okay, then this will be e to I a. This is a function xt, smooth function. This is a trajectory chosen. Okay. Yeah. So Feynman found, I think it is Feynman. Feynman actually found this ugly thing here. This ugly thing, we let n to infinity, then this will become exponential I a xt divided by h bar. Okay, this there is a jump. Okay, I admit there is a jump, and this jump is not explained in this book. Okay, but bottom line is this. This will become something, become this part become like this. So that's a quantum path integral, the consequence of path integral, where A is the action for the individual path. Feynman formulation can be summarized by a single equation. And another thing, so this integration part, this one, you have infinite number of y, infinite number of i's inserted. So this one. So that means this is all pass. So you replace this many integrals, many infinite number of inserted points, and each inserted point you have integration in the direction of x from infinity to minus infinity to infinity. So if you put all integration together, you can say this is an integration over all paths. Simply, you just call this integration all paths. Integration on all paths. So that's why now we have the probability amplitude for C12 can be written as integration over all paths exponential IA divided by h bar. So this is here, then this A is a function of one path. So there is one path. So you can do also this way. All paths means all xt. You have to integrand by all possible trajectories. Path integral formulation is not merely an elegant mathematical trick. It has real power. In fact, it can be used to derive both Schrödinger equations. Derive both Schrödinger equations and all the commutation relations of quantum mechanics. I'm not so sure here. So anyway, don't worry. So, but it really comes into its own in the context of quantum field theory, where it is the principal tool for formulating the laws of elementary particle physics. ということです。So now we can move on to lecture 10, harmonic oscillators. But I think I will do it tomorrow, okay? So, it's end. See you next time. Next time, I have to say that. Next time is tomorrow. I can show you. Susskind. This is Susskind. I have to. Today is the 10th. So next time this is the same actually. Then 編集I didn't put this this I put this one? Okay. confused. You too. I got confused. I thought I put it. Didn't I put? Now I should put it here. はい、第10回 is this one. Then let's see. これは保存して第10章 part 1 same. Next session is tomorrow 11 o'clock. Tomorrow 11 o'clock. Okay. So we go to Blue Cat. What's this? Blue Cat. Then 編集 So let's see. This is tense. Save. We delete this one. We delete. So then we copy, then here, paste. Then we delete. Okay, so then we change this one. 7. 11 o'clock. 11 o'clock. This should be okay. Then this has to be 11. So how about this? This should be okay. So see you